Very good afternoon, students. I hope all are doing good. Stay safe at home. Don't go outside unnecessarily. So we are discussing this lesson, P block elements 1. This is your second unit. We have discussed already about the boron family. That is, we discussed boron. That is the compounds of boron, that is boric acid and borane, we discussed in the last class. Today we are going to discuss diborane and the structure of diborane and alums and boron trifluoride, their preparation properties, structure and uses, all that we are going to discuss today. So how diborane is prepared, what are its properties, we'll see first. First, diborane, how to prepare diborane. So as discussed earlier, diborane can be prepared by the action of metal hydride with boron. This method is used for the industrial production. So this method, industrial production, means they will produce in the larger quantity. So diborane can also be obtained in small quantities by the reaction of iodine with the sodium borohydride and diglyme. So we have this sodium borohydride NaBH4 in reaction with iodine will give B2H6 diborane, and also we can prepare on heating with magnesium boride with HCl. Mixture of volatile boranes are obtained. So with the sodium borohydride in diglyme, it is again another reagent. There we can prepare, or otherwise you can heat magnesium boride with HCl to give this volatile boranes. Properties. So heating action, this could be asked in 2 mark or 5 mark. Borane or colorless diamagnetic compounds with low thermal stability. So which means when heat temperature is increased, they will not sustain, they will decompose. So thermal stability is very less. And diborane is a gas at room temperature with a sweet smell and is extremely toxic also. It has also high reactivity. At high temperature, it forms higher boranes, liberating hydrogen. So at 388 Kelvin in a U tube borane, 5 molecules of diborane to give higher forms of boranes, that is higher number of borane structures it will give. Same way at 198 to 373 Kelvin also it produces diborane with the liberation of hydrogen, and at 373 Kelvin in a sealed tube, and 473 to 523 Kelvin and 523 Kelvin also it prepares. Then directly in a red hot tube it gives a boron. Diborane reacts with water and alkali to give boric acid and metaborates. So B2H6, that is diborane, reacts with the water H2O, it gives a boric acid, that is H3BO3, and it also reacts with sodium hydroxide and water to give metaborates, that is NaBO2. And what is its action with air? At room temperature, pure diborane does not react with air or oxygen, but in impure form it gives B2O3 along with large amount of heat. And B2H6 reacts with oxygen to give B2O3 and water, and diborane reacts with methyl alcohol to give trimethyl borate. So you can see here B2H6 is diborane, CH3OH is methanol or methyl alcohol to give trimethyl borate. And hydroboration is again important 2 mark question. Diborane adds on to alkenes and alkynes in ether solvent at room temperature. This reaction is called hydroboration and is highly used in synthetic organic chemistry. So where this is used, this is very highly used in synthetic organic chemistry, especially for anti-Markovnikov addition. We will see what all this in organic chemistry. So reaction with ionic hydrides, that means reactive metal hydrides. When treated with metal hydride, it forms metal borohydride. So diborane reacts with lithium hydride in the presence of ether and sodium hydride in the presence of diglyme, gives lithium borohydrate and sodium borohydrate, that is LiBH4 and NaBH4. And reaction with ammonia, again very important question. When treated with excess ammonia at low temperature, diborane gives diborane diammonate. On heating at higher temperatures, it gives borazole. So you can see the structure of borazole here. At higher temperature in a closed vessel, diborane reacts with ammonia to give borazole. Then structure of diborane, repeated question this one. So you can see here in diborane 2 BH2 units will be there. So as you split this here one B H2H are there, here one B and 2 hydrogen. So 2 BH2 units are there in the structure of diborane. So listen carefully, and they are linked by 2 bridged hydrogen. So in between you can see hydrogen in common. So these 2 hydrogens are the bridged hydrogens, therefore it has 8 BH bonds. So if you count the number of BH bonds, you will be having 8 BH bond, 1 2 3 4 5 6 7 8. So 8 BH bonds are there. However, diborane has only 12 valence electrons and not sufficient to form normal covalent bond. So it has only 12 valence electron, but it needs 16 electrons. So because 8 BH bond means for one bond formation we need 2 electrons. So in that case 8 BH bond means it requires 16 electrons, but it has only 12 valence electrons. So it is not sufficient for it to form normal covalent bond. So what it does is the 4 terminal BH bonds are normal covalent. So if you see this, these four are normal covalent bonds, that is terminal BH with the 2 center and 2 electron bond, 2 center and 2 electron bond, and the remaining 4 electrons have to be used for the bridged bonds. So in the நம்ம சொன்னோம்ல இந்த ரெண்டு ஹைட்ரஜனுக்கு it 1 2 3 4 5 6 7 8 electrons have used here itself. So remaining we are left out with only 4 electrons. So on the 4 terminal BH bond எப்படி சொல்றாங்க, 2 center 2 electron. So it has 2 electron each. So it is 2 center and 2 electron. So remaining இப்போ 12 electrons 8 electrons were used in 4 BH bond. So remaining we are left out with 4 electrons. The remaining 4 electrons have to be used in the form of bridged bonds only. So அதனால தான் இங்க நடுவுல ஒரு bridge இருக்கு நமக்கு, which means they are 3 center BHB. So இதில் பார்த்தீங்கன்னா BH the 4 terminalங்கிறது 2 centerன்னு இருக்கும். Here it is BHB 3 centered. So BHBங்கிறது தான் 3 centeredன்னு சொல்கிறாங்க. Utilize 2 electrons each. Hence these bonds are 3 centered 2 electron bonds. The bridging hydrogen atoms are in plane, that is they are on plane, all are on the plane. In diborane the boron is sp3 hybridized, the boron is sp3 hybridized. Though this answer if they ask in 5 mark or 3 mark question, you have to draw the structure neatly. All the bonds are sp3 hybridized and you have to show the each hydrogen, bridged hydrogens and inside electrons, all the spin of the electron, all things should be shown very clearly. 3 of the 4 sp3 hybridized orbital contain single electron. So 3 of the 4 sp3 hybridized orbitals, so 3 of the 4 contain only single electron and the 4th orbital is empty. So 2 of the half-filled hybridized orbitals of each bond overlap with the 1s orbitals of 2 hydrogens of the 4 terminal 2c2 electron bond, leaving one empty and one half-filled hybridized orbital on each boron. So the 3 centered 2 electron bonds, that is BHB bond formation, involves overlapping of half-filled hybridized orbital of one boron and the empty hybridized orbital of other boron and the half-filled 1s orbital of hydrogen. And what are the uses of diborane? Diborane is used as high energy fuel for propellant, and it is used in reducing agent in organic chemistry, and it is used in welding torches. So the compounds of boron, if you see, if we have boron trifluoride. So boron trifluoride is obtained by the treatment of calcium fluoride with the boron trioxide in the presence of concentrated sulfuric acid. So B2O3 reacts with calcium difluoride in the presence of sulfuric acid. On heating it gives BF3, calcium sulfate and water, and it can also be obtained by treating boron trioxide with carbon and fluorine. So boron trioxide is B2O3 and carbon and fluorine to give boron trifluoride and carbon monoxide as a byproduct. In the laboratory, pure BF3 is prepared by the thermal decomposition of benzene diazonium tetrafluoroborate. And the properties, if you see, boron trifluoride has a planar geometry. It is an electron deficient compound, which means it accepts an electron pair to form a coordinate covalent bond. So the boron trifluoride is planar. So how it will be is BF3. So it is a planar compound. The structure. So it is an electron deficient compound also. It accepts an electron pair to form a coordinate covalent bond, and they also form a complex of type BX4 minus, and BF3 and H3 react together to give BF3. That is, nitrogen will donate a pair of electron to boron. So that is why they have given an arrow mark, which is a coordinate covalent bond. On hydrolysis, boric acid is obtained. So it is given, it is converted into hydrofluoroboric acid. So what are the uses of boron trifluoride? Boron trifluoride is used for preparing HBF4, a catalyst in organic chemistry. It is also used as a fluorinating agent. Next is aluminium chloride. Aluminium chloride, it is prepared by the reaction of aluminium with hydrochloric acid to give aluminium chloride, and also aluminium hydroxide reacts with hydrochloric acid to give aluminium chloride. So next is the main process is Mcafee process. Mcafee process, again a book back question. Aluminium chloride is obtained by heating a mixture of alumina and coke in a current of chlorine. So alumina and Al2O3 is alumina and coke is carbon, and reacts with the chlorine to give aluminium chloride. And on industrial scale, how they are preparing is by chlorinating aluminium. So aluminium and chlorine directly, they are reacted at 1000 Kelvin to give aluminium chloride. So their properties, so it reacts with water. So aqueous solution of aluminium chloride is acidic in nature, and also they are colorless hygroscopic substance. Hygroscopic means they will easily absorb the moisture content from the atmosphere. It produces chloride fumes in moist air. That means water is moist air. H2O is considered as moist air here. Aluminium chloride reacts to give aluminium hydroxide. With ammonium hydroxide, it forms aluminium hydroxide. So aluminium chloride reacts with ammonium hydroxide to form aluminium hydroxide. With excess of sodium hydroxide, it produces meta-aluminate. It behaves like a Lewis acid and forms addition compounds with ammonia, phosphine and carbonyl chloride. And what are the uses of aluminium chloride are? Anhydrous aluminium chloride is used as a catalyst in Friedel-Crafts reaction. It is used for the manufacture of petrol by cracking the mineral oils, and it is also used as a catalyst in the manufacture of dyes and drugs and perfumes. In Friedel-Crafts reaction, aluminium chloride enava use pandranga? Catalyst, which means it speeds up the reaction, and it is also used for the manufacturing of petrol, and also it is used as a catalyst in the manufacturing of dyes, drugs and perfumes. Next is alums. This alum question, they will ask you to write what is alum, give two example. This question was asked in government question paper this year for present 12th standard children. Government midterm question paper, this question was there, and also repeated question also. The name alum is given to a double salt of potassium aluminium sulfate. So what is an alum? Double salt of potassium aluminium sulfate, we call it as an alum. So potassium sulfate, aluminium sulfate in 24 molecules of water, we call it as an alum or potassium aluminium sulfate. Nowadays it is used for all double salts, that is any metal salt, one metal salt and again another metal salt, 22 molecules of water, where M is an univalent metal. That metal should be an univalent metal ion, or it should be a trivalent metal ion. So examples, if you see potash alum, that is K2SO4, Al2SO4 thrice 24H2O is potash alum. Sodium alum is again the same formula only. Instead of potassium sulfate, you will have sodium sulfate there. And ammonium alum is ammonium sulfate, you will have there. Chrome alum is potassium sulfate with chromium sulfate, you will have. And alum in general are more soluble in hot water than in cold water, and in solution they exhibit the properties of constituent ions. And their preparation, the alunite, alum stone is naturally occurring form, and it is K2SO4.Al2SO4 thrice 4 AlOH thrice. When alum stone is treated with excess of sulfuric acid, the aluminium hydroxide is converted to aluminium sulfate. It will be converted to aluminium sulfate. A calculated quantity of potassium sulfate is added and the solution is crystallized to generate potash alum. So it is purified by recrystallization, that is K2SO4 Al2SO4 thrice and 4 AlOH thrice plus 6 H2SO4, which means this alum we have to take as alum stone. So what is this K2SO4 Al2SO4 4AlOH thrice is alunite, which is an alum stone. From there, if we treat that with excess of sulfuric acid, we will get the aluminium hydroxide, which will get converted into aluminium sulfate, and we have to take a calculated quantity of potassium sulfate with that aluminium sulfate, and so that it will start to crystallize as alum. Clear? Next is their properties. So alum reacts at the 500 Kelvin. That is, potash alum is a white crystalline solid. It is soluble in water but insoluble in alcohol. So this alum is nothing but which is used as a water purifier. So we use this in houses also, and it is also used in some of the houses. In the entrance they will tie this and keep on the for some ritual purposes. People tie this on the entrance of the houses, and also this is used for the purification of water. That is alum here. Actually, the aqueous solution is acidic due to the hydrolysis of aluminium sulfate. It melts as 365 Kelvin on heating. At 475 Kelvin it loses water of hydration and it starts to swells up. The swollen mass is known as burnt alum. So the swollen mass is known as burnt alum. Heating it to the red hot tube, into potassium sulfate, alumina and sulfur trioxide. So what will happen? They will start to decompose. Potash alum forms aluminium hydroxide when treated with ammonium hydroxide. So it is uses again very important, 2 mark. First is purification of water and waterproofing and textiles, and used in dyeing, paper, leather and tanning industries, and as a styptic agent in arrest the bleeding. So these are the uses of alum. Uses also, again it has been asked at this time, what is alum? Give 2 example and write its uses. Altogether was 1 question. So it is very important.